Welcome to this Forge College Explainer. Let's just dive right in, shall we? If you've been following along with our From EVM to SVM, transitioning from Ethereum to Solana track, you know we're right in the thick of the capstone project. In our last lesson, Overview and Strategy for Porting Smart Contracts, we mapped out our source contract responsibilities and, set up some really concrete compatibility checkpoints. But before we actually start translating that code, we absolutely need a reliable place to do it. Think of this explainer as building the ultimate, indestructible laboratory for your code. So today we're unpacking the development environment and tooling for porting.
All right, here is our engineering survival guide for today. We're going to build a reproducible, bulletproof machine to test our EVM to SVM porting. We'll tackle the environment drift gremlin, blueprint our project skeleton, write an idempotent setup script, fire up a smoke test, and then learn how to use artifacts as our absolute single source of truth. Let's get to work.
Part 1. The environment drift gremlin.
So, every good story needs a villain, right? And ours is that dreaded, well, it worked on my machine yesterday syndrome. We call this the environment drift gremlin. Look, when you're porting smart contracts, you are going to be iterating constantly. You'll compile Rust, run local tests, tweak translation patterns, compare execution traces, the whole shebang. But here's the catch. If your environment shifts between those iterations, say your Rust compiler silently updates in the background, or a system dependency just goes totally out of sync, your test comparisons suddenly become useless noise. If you've ever found yourself fighting your own computer instead of your code, you know exactly what this pain feels like. Instead of validating your actual smart contract logic, you end up wasting precious hours chasing these environmental ghosts. So we've got to lock that down tightly from day one.
Moving on to Part 2, Blueprinting the Project Skeleton.
To banish those ghosts for good, it's time to unroll the engineering schematic and establish a rock-solid workspace layout. Notice how minimal yet entirely purposeful this structure is. Every single folder has a distinct job that cleanly maps to those EVM migration checkpoints we established before. We've got the setup folder to hold our reusable, version-locked scripts, so literally anyone on the team can spin up the exact same environment. The Programs folder houses our Rust-based Solana program skeleton, mirroring your source module boundaries perfectly. Then the Tests folder is dedicated strictly to our local integration and smoke tests. After that, we have Artifacts, which will hold our compiled binaries and JSON outputs for super strict version comparisons, and finally, Docs for those essential developer notes. It's clean, it's mapped out, and it completely prevents workspace clutter.
Part 3. The Impedant Setup Script. With our folders perfectly in place, let's introduce our ultimate weapon against that drift gremlin. I kind of like to think of it as a very polite but incredibly strict robot butler, the setup script. Now, you'll hear the word idempotent thrown around a lot in engineering circles. I know, it sounds a bit intimidating, but it really just describes an operation that can be applied multiple times without changing the result beyond the initial application. Simply put, an idempotent setup script checks if a tool is already installed before it tries to blindly install it again. This makes it totally safe to run over and over without causing messy path overlaps, duplicating files, or completely breaking your local environment.
Let's actually compare these two approaches side by side. A brittle script blindly tries to install everything, every single time you run it. It overwrites your custom paths, ignores existing configurations, and inevitably, it breaks something crucial. Our idempotent script, on the other hand, is smart. It actively checks the current state of your machine first. It strictly locks into specific, tested versions. And honestly, most importantly, if it finds a mismatched state it can't safely resolve, it fails loudly and immediately, alerting you to the exact problem. Basically, it only cleans up the kitchen if it's actually dirty.
So what does this look like in practice? Well, our bash script will first check if the Rust toolchain and the solana-test-validator already exist on the machine. If they're missing, it installs them. But it doesn't just pull the absolute latest version off the internet willy-nilly. It locks them down to exact versions. For this specific exercise, we're pinning Rust to version 1.65.0 and Solana to 1.14.17. By designing the script to exit immediately on any error, we guarantee that reproducibility requires early, obvious failures. We absolutely do not want silent, sneaky continuation that ends up ruining your project 3 days later.
All right, Part 4, firing up the smoke test. Now that our environment is locked, loaded, and totally reproducible, let's transition to a low-stakes engine rev. We're going to safely fire up our local validator and run a quick smoke test. The elegance of this setup really lies in its sheer simplicity. Once your script runs successfully, compiling your minimal Rust program skeleton into a .so binary is literally as simple as running cargo build --release. If this command succeeds without throwing a giant wall of red text at you, it proves your entire toolchain works perfectly. And the best part? You get this validation without having to write a single complex line of smart contract translation logic yet.
The smoke test itself is a really straightforward, deliberate sequence. First, we start the solana-test-validator in the background. Second, we deploy that freshly built binary program. Third, we record the deployment output, meaning the program ID and the console logs, straight into a JSON artifact file. And finally, we cleanly kill the validator process. So you start the engine, you record the hum, and you shut it down cleanly. Leaving absolutely no lingering background processes guarantees nothing is going to mysteriously break your machine on the very next run.
Part 5. Artifacts. The single truth. Let's circle back to step 3 from that smoke test sequence for a second. Recording the artifact. This brings us to the crucial flight recorder of our application, the artifacts folder. Let's look at why these specific outputs are your absolute ultimate source of truth for behavioral equivalence. The deploy JSON tells us exactly what happened the moment we deployed. The validator process text file proves the actual environment was running exactly as expected. And most importantly, the baseline deploy JSON serves as our behavioral baseline. When we start changing code later on, we're going to constantly diff our new outputs against this exact baseline. If they match, boom. It proves our porting was successful and behaviorally identical.
But there is a vital rule you'll really want to remember here. You must normalize timestamps and ephemeral identifiers before saving. Think about it for a second. If your JSON file saves the exact millisecond of the deployment, it will literally never match the next time you run it, even if the underlying code is 100% identical. Your comparison dips will just light up like a Christmas tree with false failures. So you have to write your scripts to strip out or replace those ephemeral timestamps with fixed, predictable placeholders. This is what keeps our baseline pure, calm, and perfectly deterministic.
Part 6. Next steps for porting.
Okay, we've designed the schematic, we've built the lab, we have effectively banished the gremlins. Let's quickly summarize the golden rules of our newly built environment before we actually get our hands dirty with active code porting. Following these 4 pillars will quite literally save you countless hours of frustration. Number 1, pin everything. Your toolchains, your crates, your specific dependencies. Number 2, prefer idempotent automation so your setup scripts are always safe and flawlessly repeatable. Number 3, run deterministic tests by proactively stripping out those random variables and timestamps. And number 4, always save your baseline artifacts. These rules aren't just polite suggestions, they are your absolute primary defense against the dreaded "it worked yesterday" problem.
So I'm going to leave you with this question. Is your local environment truly drift-proof right now? And are your artifacts genuinely ready for translation? Because in our next lesson, implementing porting patterns, we're going to use this exact robust skeleton to start moving logic from EVM directly to SVM, confidently validating every single step of the way. Make sure your lab is ready to go. To dive deeper into this subject, grab the code snippets from today, and explore more Web3-related topics, be absolutely sure to visit forge.college. This has been a Forge College Explainer. Keep building, keep testing, and I'll catch you in the next one.